Well, hello to everyone. My name is Daniele, and I work in Belo Horizonte in IHM Stefanin. And I will tell a little about the leak detection system using machine learning techniques. But first of all, I would like to thank you for this opportunity for telling my real machine learning story, as Kappes is to tell real-world machine learning stories. And I would like to tell you a little bit about my real machine learning story and how I ended up on this field. The first contact that I had with artificial intelligence was on the college. I did a subject called neural networks, and I thought it was the most difficult subject that I have ever learned on the college. Actually, I gave up on the subject, and I never thought that I someday could work with this or learn something related to this. And after I tried to do this subject, I was looking for an internship, and I got this interview opportunity on IHM Stefanin. And I remember that the interview asked me about what did I think about artificial intelligence. And what do you think that I answered to him? I told him that I thought it was really awesome, but I really believed it was very difficult. Then this was 2 years ago, and then I had the opportunity to work on different projects on machine learning. I had the opportunity to work on this project that I will tell you about, and another projects like in iron ore company with flotation process. And I would like to tell you the motivation of this project, how did we solve the problem, and what did we exactly do? Well, what was the motivation of this project? We had this client 2 years ago in 2016, and that had experienced 2 leak occurrences within 1 year in their slurry pipeline. I don't know if you know the process of iron ore beneficiation, but there is, at the end of the process, this slurry pipeline, and they had 2 leak occurrences, and there was an environment hazard. The process data was not recorded during the leak occurrences, and then the sensors were not running, so the client didn't know how was the behavior of the pressure, the density, and the flow on the pipeline. So the big challenge was to know what was the anomalous behavior, what would represent a leakage on the pipeline. Well, how did we solve the problem? First of all, if it was with transparency, because we told the client that we didn't know how to solve the problem, but we had an idea using machine learning techniques. So the client knew that we could solve the problem, or we had an idea on how to solve the problem. We used an open source and an interpretable machine learning solution. So the client knew everything what we were doing, and the client was able even to do some improvements on the model during the project and helping us on solve the problem. What did we exactly do? So if you look in the literature, you can see that in pipeline leak detection methods, you can have hardware-based methods, biological methods, and software-based methods. In hardware and biological methods, usually the solution, it has a high cost, and it's for bigger pipelines, more than 10 kilometers. So as the leakage occurred on the end of the process, it wasn't the product of the company, it was the slurry, the waste of the iron ore they didn't want a solution with high cost. So visual acoustic sampling and negative pressure, the cost was too high to implement in a small pipeline, as was of the client. So in software-based methods, we can have mass or volume balance, pressure point analysis, but we focus on flow and pressure change in building a dynamic model, because we were dealing with data, and as I said, the pipeline was smaller than the usual. It was less than 10 kilometers. So here's a schematic of the pipeline. Actually, the pipeline starts here and ends here. So we have a tailing, the tailing tank. We have two pump stations, the pump in series 1 and pump in series 2. And at the beginning of the pipeline, we have pressure sensors. Also, we have density sensor and a flow sensor. Along the pipeline, we have two more pressure sensors. So the system basically works as detection of leakage between 2 points of measurements. We used the data that was already recorded during the past. But as I said, we just had the normal behavior of the pipeline. So I'll show you how the system works. We have the pipeline, then we record the process variable. We record in the SQL database, and then we run the analysis on this platform called NIME. I don't know if you know. And what we did, we simplified the pipeline as this figure here. So using the Bernoulli equation, we can know that the conservation of energy says that the energy in one point of the pipe should be the same or almost the same as the energy on another point of the pipeline. So using the Bernoulli equation, we know that pressure in the point A over the fluid density is a function of the pressure on another point of the pipeline, on point B, over also the density fluid, and also is proportional to the squared flow. So with this, we ended up with a model that is dependable on the pressure, the flow, and the density of the fluid. And then we train our model on normal behavior of the pipeline without leaks, so we can understand what is the normal behavior of the process variable, the pressure, the density, and the flow. So if we apply this model that was trained offline, we apply in an online way. So if we have, here we have the data process, and then we have our calculation of our model. If the system found a difference too big between the real data and the calculated model, the system sent an alarm. This alarm is also recorded in the SQL database and is also sent to the PLC, the Programmable Logic Controller, through OPC. So the operators, the plant operators, can know if there is a leakage alarm or not. So what was the challenge that we faced during this project? First of all, it was which data should be used. Because when we were on the project, we didn't know how much amount of data would represent the normal behavior of the pipeline. We didn't know if it was 1 month of data, 3 days, 10 days. So we tried different models. We used different scenarios, like we didn't know if we should use the pressure when the pressure was more stable, or we should use also the pressure when the pressure was unstable. So at the end, we found out that the best was to use around 3 days of functioning of the pipeline. So here at the left, we have the training data. So our features is squared flow on red, and the pressure over density in the point of the pipeline on purple. And at the right, we have the validation test, the validation set with real and model, showing that these two features could explain well the behavior of the data process, the process variable on the pipeline. The second challenge was amount of false alarms, because as we understood the behavior of the process variable, any unexpected behavior, the system interprets like an alarm and a leakage. So we ended up with 2 main scenarios. The first scenario was a best performance of the system. So the system had a high leak detection accuracy, so the system could detect even small leakages around 30 cubic meters per hour, but the system also accused a high amount of false alarms. So it was more than 15 alarms per month. So it was too many alarms to the plant operator to verify during all the month. So the second scenario we got was a good performance. The leak detection accuracy was a little bit lower, but the amount of false alarms was acceptable. It was 3 to 5 false alarms per month. And the client said that it was an acceptable amount of false alarms. The third challenge was how can we validate it? We had 2 options: wait for the system to have a true leakage, or we could test it with a true leakage simulation. So we did a simulation of the pipeline to see if the system was capable of detecting or not the leakage. Before we did the test, the system was with 1 false alarm per month. The model performance here was around 0.9 of coefficient of determination. And the leak detection accuracy was over 100 cubic meters per hour. Usually the pipeline was running with 1,000 cubic meters per hour, so this leak detection accuracy was about 10% of the flow on the pipeline. And as you can see here, we have the real data and the model, the calculations of the model, and when the system found a huge difference between these 2, model and real, they accuse an alarm. So the key of the project was to know what difference would represent a true leakage. So that's why we did the simulation on the pipeline. So here, as you can see, this is the pipeline, and I don't know if you can see, but there is a drain here between 2 points of measurements of pressure. And basically, what was the leakage simulation? We opened this drain, so the slurry flow was deviated to a hole in the ground. And this deviation of the slurry represented like a leakage on the pipeline. So we run this and looked to the process variable to see what was the system response. This was the response of the system. As you can see, there was 3 alarms because we opened the drain 3 times. So here on the first time that we opened the drain, we can see that there was a huge difference between real and model, and just around 5 or 10 minutes after, the system accused an alarm. Then we closed the drain, so the model and real, it was almost the same. And the second time that we opened the drain, there was another huge difference between model and real, and then the system accused another alarm. This one was the third time we opened the drain, and also the system accused an alarm. So after this leakage test, we could retrain our model and actually adjust this difference that the system interprets as a leakage. We ended up with 3 to 5 false alarms per month, with a model performance in around 0.75 of coefficient of determination. So as you can see, it's lower than the first one because we used more generalized data to represent the functioning of the pipeline. And the leak detection accuracy was around 70 cubic meters per hour. So it was less than 10% of the flow that runs inside the pipeline. And at the end of the project, we had some conclusions. The first one that it was that everybody wins with a co-creation business model. Because as I said, we didn't know how to solve the problem. We had an idea and told to the client what was the intention of the project. And the client understood the challenge during the project. We learned that simple solutions can solve simple problems. As you can see, the machine learned part of this project was just a linear regression, as I said, based on Bernoulli equation. It wasn't a complicated algorithm. The model is locally dependent on the data. So if we have another pipelines, we have to use the data recorded that represents this pipeline. So it's not generable to any kind of pipeline. At the moment, 4 pipelines are monitored by this system at this company, at this iron ore company. And there are the next steps. We can extend its capability to detect the exact point of the leak in the pipe, because as I said, the system doesn't say where is occurring the leakage, just say that there might be a leakage between 2 points, 2 measure points. We could try to reduce model dependency, and we also want to test the model for bigger pipelines, bigger than 10 kilometers, because as I said, to bigger pipelines, there are another solutions with high cost, but also with higher precision. So we could try if this system works also in bigger pipelines, bigger than 10 kilometers. And that's all. Thank you. I hope you enjoyed. Do you have any questions?
Hi, very nice talk, by the way. As you mentioned several times about this co-creation, like project, and the machine learning, as you said, it wasn't so complicated. I'd like to ask you about like this management of this project. It was together with the client. So how did you guys like visit the facilities and talk with the operator's crew, or just like managerial?
Yeah, because this client is an old client of IHM, so we already have contact with the client. It was like IHM has been doing projects for this client more than 20 years, so it was easier to talk to the client and explain the situation and convince the client to try to solve the problem, because another project that is not related to machine learning that IHM have gave to them in automation industry. you know.
So your company is more an engineering company
Yeah.
that is starting to use machine learning?
Yeah, it's usually automate industry, like 20 years. So just for now, we are starting with machine learning projects. We had an opportunity to do also prediction of silica on flotation. And in the same way, we said that we didn't know how to solve it and try to solve the problem. So it's just now that we are having machine learning projects.
Okay, thanks.
I'm interested in your story about having this barrier with neural networks in the beginning and ending up working with that. In your opinion, what was the problem that you faced? Was how it was taught?
Yeah, the first time that I did neural networks, I thought I was at the end of the college, so I didn't have too much time to really try to learn, so I did just for curiosity. And I think it was the way that it was taught, because for me, I believed it's easier to understand if I, how can I say, go to and do my courses and not just to learn in a normal class. For me, it's different to learn on the college and just learn for myself. I don't know if it's clear, this. And also, I had an opportunity to do my final paper on the college with neural networks. And the part that really helped me to go to this machine learning world was this guy that did my interview on IHM, Stefanin, because even as I was saying to him that I thought it was too difficult, he believed that I could finish my final paper, and I learned that I could really understand if I wanted to.
Hi. What kind of algorithm did you use it to detect the anomaly? Did you use a deep learn, or maybe using classification, or use it like anomaly detection?
So it was just a linear regression, because what we did was to predict it, like the energy. We predicted the pressure over density in one point of the pipeline based in another one. So it was a regression problem, simple regression problem with linear regression based on Bernoulli equation. Thank you.